Hello. In this session, we'll mainly address important terminologies used or identified or generally discussed while talking about CPU scheduling in operating systems. And these terminologies play an important role while addressing different scheduling algorithms or scheduling methods adopted by the operating system. So we'll address them one by one, and they are really important terminologies, as I stated. So first terminology is arrival time. This arrival time refers to the time at which process generally arrives in the ready queue. And once it arrives in ready queue, that means it is eligible for execution on the CPU. Now, this generally is considered as a key input sometimes to determine order of uh, the execution for the processes by the scheduling algorithms. Every operating system generally records this time when a process actually enters in the system. Let us say, as an example perspective, we have three processes P0, P1, P2, and operating system recorded their arrival time say as 0, 1, and 4. What are the time units? In this case, I was in milliseconds. Now, this order can be considered by some of the scheduling process methods or scheduling algorithms to determine in what order the process should be executed. So sometimes, like if algorithm talks about arrival time, scheduling algorithm talks about arrival time, then ultimately this arrival time would be important. Next is burst time. This burst time is amount of time or total time a process needs to execute its tasks on the CPU. Note here that burst time never considers waiting time or maybe IO operations, time taken for IO operations or other overheads. This generally would be counted or accounted only for the amount of time used when CPU is allocated. And that is the reason why it is also called as execution time or service time. Let us say, as an example perspective, we have three processes P0, P1, P2 respectively. And we know that, say, each one of them was given time respectively as 5 time units, 3 time units, and 7 time units. So, like this burst time, if we know that from the CPU execution perspective, some algorithms may consider this burst time also to decide what should be the order of execution. Completion time, it refers to the time at which process completes its execution and terminates or exits from the system. It is always essential to know this computation of completion time because this can help us evaluating the performance of scheduling algorithms. Further can be used for optimizing the efficiency. This completion time, as I stated, would be total time taken for a process to finish its execution. Say we have P0, P1, P2 arrived at 0, 1, and 4 time unit respectively. And if we know, say, their burst time, 5, 3, and 7 respectively, as a time units perspective. So completion time in this case can be computed as 5 millisecond, 8 millisecond, and 15 milliseconds. Because at this particular time line, like starting from 0, they would be finishing their execution. Next is turnaround time. This turnaround time measures the total time taken by the process to complete execution from the time it arrived till the time it exits. It is an important indicator used in computing system efficiency and user satisfaction. The total time a process would be spending in the system from arrival to completion, also like we call it as turnaround time. So if we have to compute turnaround time, then we have to compute it like this: completion time minus arrival time. Say we have again P0, P1, P2 as a processes. Their arrival times are known as 0, 1, 4. Their burst time is known as 5, 3, and 7 respectively. So as we if we compute completion time, then it would be like 5, 8, and 15. Now to compute this turnaround time, as we stated, we will subtract arrival time from the completion time. So we get 5 milliseconds, 7 milliseconds, and 11 milliseconds as an turnaround time. Now, using this turnaround time computed for separately for each process, one can compute average turnaround time by taking sum of the turnaround time respectively for the processes divided by number of processes. So in this case, like 5 plus 7 plus 11 divided by 3 would be 7.66 milliseconds, or whatever the time units that is considered there. Next is waiting time. This waiting time is again one of the critical performance metric used by most of the scheduling algorithms. It measures the total time process spending waiting in ready queue before it actually gets access to the CPU. Now in turnaround time, what we saw that it includes execution time. Here, waiting time only focuses solely on the waiting period. And it is always good, like we should minimize waiting time so as to improve the system responsiveness and user satisfaction. So waiting time would be computed as waiting time equal to turnaround time minus burst time. Again, example perspective. Let us say we have three process P0, P1, P2. Their arrival time respectively 014. Say their burst time is 537. So as we computed completion time as 5, 8, and 15, we also computed their turnaround time in the previous case 5, 7, and 11. So waiting time would be now turnaround time minus burst time. So 5 minus 5, 0, 7 minus 3, 4, and 11 minus 7, 4. Correct. So, like if we consider this waiting time computed for every process separately, one can compute average waiting time by summing the total waiting time for all the processes available there divided by the number of processes. So, in this case, like 8 by 3, 2.66 time unit or milliseconds. Next is response time. Response time is again a duration between arrival of a process in the ready queue and the time it starts execution on the CPU for the first time, definitely. Now, this would be a measure how quickly a system is responding to a new task or a request. So, response time would be computed. For that purpose, we will require first execution time when exactly it got the access of CPU minus arrival time. So, let us say we have P0, P1, P2 arrived at 0 to 4 time unit respectively, and their burst time known as 538. So, when P0 arrived, CPU was allocated and P0 started its execution. It finished, say, at 5. But before it finished, P1 and P2 arrived. So P1 arrived at 2. Correct. So, like once P0 completes, P1 would be given chance. So that's why P0 completed at 5. So that's why P1 would be starting, or P1 would be allocated CPU at 5. So that's its first execution time. So 5 milliseconds. Now we know that P2 also arrived at 4 milliseconds. Okay, like before P0 finished. But as P1 started already, so like P1 would be finishing at considering its burst time at 8 milliseconds. That's why P2 would be given chance to first start its execution at 8 milliseconds. That's why their first execution timing would be 0, 5, and 8 respectively. So ultimately now we have to compute response time. Now response time would be first CPU execution time minus arrival time. So if we see here 0 minus 0, 0, 5 minus 2, 3, and 8 minus 4, 4. So this is the response time respectively. So even if you want, you can compute average response time. Throughput generally refers to the number of processes or a task that a system can complete in a given time frame. It is generally measured in terms of per second, per minute, or similar kind of units. Now, let us say we have three processes, P0, P1, P2. Their arrival times are known, say 0 to 4, and their burst times are also known. Now, if we consider the burst time for each one of them, so total time taken by these processes, okay, would be like say 5 plus 3 plus 8, 16 time units. So you can compute, like for example, 3 by 16 processes per time unit. depending upon the time unit taken, whether it is millisecond or second or whatever. CPU utilization would be percentage of time the CPU is spending executing processes compared to the total available time. So computed as CPU utilization equal to the time CPU is busy divided by the total time the system is up multiplied by 100%. Next is starvation. It occurs when a process or task perpetually gets delayed or denied access to the resource because there are other processes to whom the access is given, or they may be always favored. So this starvation can lead to poor system performance, unfair resource allocation, and even system failures in extreme cases. So mostly caused by priority inversion, resource contention, and unfair scheduling policies. And the last thing, convoy effect. This is considered in process scheduling, and it occurs when a long running process, typically a CPU bound, holds up for shorter processes, leading to inefficient CPU utilization and increased waiting time. And this happens because all other processes have to wait for long running processes to complete before they can execute, even if they require only small amount of CPU time. Because of this convoy effect, shorter processes experience unnecessary delay. That's why waiting time is increased. IO devices remain idle while waiting for CPU bound processes to finish, leads to poor resource utilization. The overall number of processes completed per time unit decreases, and that's the reason, like one can say, the system throughput would be reduced. And as the system may appear sluggish as shorter tasks are getting delayed behind longer ones, that's why there can be seen as unbalanced workload distribution. So these all are important terminologies. Next session, we'll be talking mainly about different CPU scheduling algorithms.